Hello there. This is the first video for a short series that I'm making for my Principles of Functional Programming class. Basically, students were hoping for something that goes beyond what the books show, so I decided to go with some videos since I'm already making a bunch of them for my Scala classes. So when I teach the functional language class, I like to use two languages, and this semester I'm using Scheme and Haskell. And I start off the semester in Scheme. And the reason that I start off in Scheme is because it is, in my opinion, at a fundamental level, a very simple language kind of to grasp the syntactic aspects of. So you can be up and running in Scheme very quickly, and you can write little programs. Now, getting your brain around the details and understanding how to write decent programs in Scheme, well, that's a different matter, and that's why I'm making these videos. The environment that I'm working in is actually called Dr. Racket. So Racket is kind of a superset of Scheme. So Scheme is a descendant of the Lisp language, and as people like to joke, Lisp, the common phrase is that it stands for lots of insipid, stupid parentheses. There are lots of parentheses in both Scheme and in Lisp. And the thing about Scheme is that it really has kind of one fundamental structure. This isn't quite true. I'm oversimplifying here, but this is the first video. I can oversimplify. And that is the list. So a list is just a bunch of parentheses inside, or a bunch of values inside of parentheses separated by spaces, and they can be all types of things. This is how data is stored inside of Scheme, is inside of these lists. We'll learn there are some nuances to that, and there are other ways of storing data, but this is the most basic way to do it. In addition, it turns out the lists are how you do programs in Scheme. And so, for example, if I want to add 3 and 5, in Scheme I have parentheses plus 3, 5, and I get 8. So some things that should jump out to you automatically are there are parentheses. Everything goes in parentheses. The plus sign is not between the 3 and the 5. The way that Scheme works, its syntax is what's called a prefix syntax. So all of the operators go in front of their operands, and everything has to be fully parenthesized. So we're going to have lots of parentheses. Fortunately, you can also alternate and have some brackets. Now you might be wondering up here what this was. What I typed in earlier is actually short for, sorry, I left out some parentheses. That will happen occasionally. Short for this, the single quote is short for the quote function. The way that Scheme normally interprets a list, if you just input it like this, is it evaluates each of the arguments. Once again, they're space separated, and it takes the first one and says, okay, well, this needs to be a function call, and I'm going to apply this function to these other values. Well, so if I just try to do this, I'm going to get an error message. And I get an error message because what I was telling Scheme to do here was to say, okay, take the function 1 and apply it to 2, 3, and 4. And Scheme comes back and says, 1 isn't a function. They use the term procedure through here, but basically 1 is just a numeric value. So that's not happy. If I want to have it so that it's not evaluated in that way, I have to quote it. And so the whole purpose of this quote function is to give you back exactly what is quoted. In some ways the name makes perfect sense here. And so if I want to get back a particular list, I can put it in quotes. And lists can be nested inside of one another. Notice that I don't need another quote here because this was quoted. This whole thing is processed or is just taken as it is without any processing or the application of any functions inside of it. In fact, it's interesting to notice that that comes back quoted as well. One thing about this prefix notation, and you might be tempted to go, why would anyone do that? One particular advantage is that you can have as many arguments as you want, whereas with math we normally use an infix notation. In theory, the scheme developers could have done infix for math and prefix for everything else. And in fact, in a certain sense, the prefix, when you're used to doing functions, you see them like this. That would be f of x the way you're used to seeing it. In scheme syntax, it would just be like this. This is f of x. Just this parentheses comes before the name of the function. That's the only real difference. And instead of being f of x comma y, it is not commas, and it would just be f x y to generate a call like that. Okay, so that introduces lists. You've seen plus. As you can probably guess, there's a minus, there's a multiply, all the types of things that you're used to for simple math operations. What about dealing with lists? So if I have, once again, my list 1, 2, 3, and I want to get just the first element off of that. Well, there are two main list operations for getting parts of it. One is called char, and char gives you the first element of a list, so it pulls off just this piece. The other function is called cdr. Oops. And the cdr gives you everything after this. In many other languages, these would be called head and tails. So the head of the list would be the 1, and the tail of the list would be the list 2, 3. And so if I wanted the second element of this list, I could call the char of the cdr of the quoted list 1, 2, 3. And that gives me back the 2. There are shortcuts for this because you combine these things quite a bit. Turns out that if you just put the A's and D's in the order that they would have been here, so there's the char of the cdr, that can be written just as the cdr. If I wanted the 3, that would be the char of the cdr. So that's the cdr. And that is just short for char cdr, and then I would have another cdr around the 1, 2, 3. You can also build lists using an operator called cons. Now, everything that's a list ends with the empty list, which you can refer to as the empty list or null. And so if I do a cons of 2 onto the empty list, I get back the list that just has the 2. I can cons a 1 onto the cons of the 2 onto the empty list, and then I get that. Okay, and so those are lists, and so cons builds things up. It just adds on to the front of the list. Char gives you the front of the list. Cdr gives you everything other than the front of the list. You might notice that I keep having to type in quote 1, 2, 3. And inevitably, if you're watching this, hopefully, because I am assuming you have some programming knowledge, if you're watching this, you know that it might be really nice to have a name for that. And one way that we can bind names in Scheme is to use define. So this is a new syntactic element for us. I can define, and I'll just call it LST, to be maybe 1, 2, 3, 4. And then I can take the char of LST, and I can take the cdr. All right, let's just do the cdr of LST, and I can do the cdr of LST to get the 2, etc. Okay, so so define will allow you to give names to things. Con, scooter, car. These are our basic operations, and everything goes inside of a list. You do have your normal math functions, and in fact it is worth noting, just at this point we can already kind of see this. So that is a billion times a billion, and I actually get the number with all the digits out there. If you try this in most other languages, you will run into problems. So there's your basic introduction to Scheme. I'll come back in the next video, introduce conditionals, maybe introduce lambda expressions, and then put them together, and we'll start writing a little recursion so that we can actually do some logic.